All right, question 5. This will be solving differentials. So a lot of the material that we just did before we left for home. So it says the rate at which a baby bird gains weight is proportional to the difference between its adult weight and its current weight. At time t equals 0, when the bird is first weighed, its weight is 20 grams. If B of t is the weight of the bird in grams at time t days after it's first weighed, then you're given your rate of change for the weight of the bird with respect to time, 1/5 times 100 minus b. Let y equal b of t be the solution to the differential equation above with initial conditions b of 0 equals 20. Part A says, is the bird gaining weight faster when it weighs 40 grams or when it weighs 70 grams? Explain your reasoning. So all we want to do is plug in for B here, okay? Because when you're being asked, is the bird gaining weight faster? That means we want to know, is our rate of change greater at 40 or at 70? Okay, and remember, that's what this is. This is our rate of change of the bird's weight with respect to time, okay? So we just want to evaluate this at those two different times and see which one is bigger. So with part A, we're going to evaluate dB dt at 40. And that means its rate of change is 12 when it weighs 40 grams. Okay, so its rate of change is 12 grams per day. And then when it weighs 70, right? 70? Yes. When we plug that in, it's gaining at a rate of 6 grams per day, okay? So since 12 is greater than 6, and we can say the bird is gaining weight faster when it weighs 40 grams compared to when it weighs 70 grams. Okay, so it's growing at a faster rate in the beginning. Okay, part B, find the second derivative. So you see that d2b, this right here, that's our notation for our second derivative. You guys have seen that in terms of b. And we're going to use that second derivative to explain why the graph of b cannot resemble the following graph. Okay, so we're going to start by finding our second derivative. So if this is our first rate of change, so the change in the bird's weight with respect to time is given as 1/5 100 minus b. We want to take the derivative of both sides with respect to time. So on the left side, that's where we get the d, our second derivative of b with respect to time, will equal, so if you look here, the derivative of this, you can even think about it as distributing that 1/5 through, so it's the same thing as 20 minus 1/5 b. That's going to leave us with negative 1/5 times, since this is with respect to t and the variables don't match, you have to use chain rule, times the derivative of b with respect to t. Okay, So if we keep going and plug in what dB dt is, it gives us negative 1/25 100 minus b. And then it says to explain why the graph of b cannot resemble the following graph. So if you look at that graph of b, it's this one right here. You got to think, why can it not be that? So looking at this, notice here, concave up. Notice here, concave down. Okay? So look over here, and for the values between 20 and 100, because that's what we're given from the beginning, it starts at 20 and tops off around 100. Think about if you look for those b values, that are less than 100 or greater than or equal to 20, is our second derivative positive or negative? Okay, so no matter what, if we plug in 20 or any number close to 100, it's going to be a positive output times a negative 125. So for b values of greater than or equal to 20 grams and less than 100, our second derivative is always negative. Therefore, b must be concave down for those values. Okay, in this graph has a portion where it is concave up. All right, last part of this says to use separation of variables to find y equals b of t, the particular solution to the differential equation with the initial condition b of 0 equals 20. So we're going to go back to what we started with. And what we started with was the rate of change of the bird's weight with respect to time is equal to this. And when you see to use separation of variables to find the solution to our differential equation, that means we want to get our b's to one side, everything else to the other. So I'm going to do that by dividing by that 100 minus b. So I get this equals 1/5 dt. And once I have that separated, I can introduce an integral symbol to both sides. The right side, I just get 1/5 t plus my constant. On the left-hand side, since our derivative of the denominator is not 1, we do have to use substitution, okay? So I'm going to do that off to the side. I'll do it in black. So if I let u equal 100 minus b, du db will equal a negative 1, and db equals negative du. Okay? So if we plug that back in, I will have the integral of 1 over u times a negative du. So I'll actually throw my negative out front. And when I integrate that, now I'm good, and I'll have the natural log of the absolute value of u technically plus c, but we don't need it because my plus c is on the other side. And that will equal the natural log of 100 minus b. And so that's how we can get to that point. And then this whole problem resembles with this part of it is the Newton's law of cooling when we went through this in class and you guys had some homework questions on it. So now that we have this, we want to solve for C, knowing that B of 0 equals 20. So what is that telling us? It's telling us when time equals 0, the weight of the bird is 20 grams. So we can throw that in there and we get the negative natural log of 80 equals C. So there's our constant. And if we go back through and plug that in, I'm going to divide by a negative. And now I can convert this to exponential form. So it'll be e to the negative 1/5 t plus ln of 80 equals 100 minus b. And I can separate that. So I will have e to the negative 1/5 t times e to the ln of 80. And e to the ln of 80 is just 80. And I want to solve for b, so I'm going to move b to the other side. And I'm going to have 100 minus 80 e to the negative 1/5 t power. So our function b with respect to time, or in terms of time, sorry, will be 100 minus 80 e to the negative 1/5 t for values greater than or equal to 0. So this equation gives us the weight of the bird with respect to time, and I think time was in days. So after however many days after the bird was born.